Hello students, welcome to this lecture. In the last lecture, we were discussing the application of linear variational method in chemical bonding, and within that we are looking at the molecular orbital theory, in particular the molecular orbital treatment for hydrogen molecule. We discussed that molecular orbital theory suggests a very simple way of constructing trial function, that is, the molecule consists of several atoms. So, linear combination of these atomic orbitals would give rise to the molecular orbitals, and so that becomes the recipe for constructing our trial wave function. We did this for hydrogen molecule, but in this lecture we will extend our discussion from hydrogen molecule to other larger systems, because in case of hydrogen molecule we had only 1s electrons, but there are many interesting things that come up when we have electrons in other orbitals. So, that is why we will first consider the diatomics, and then we will go for the polyatomics, and then we will see how molecular orbital theory follows a very simple recipe that constructs the linear combination of atomic orbitals and then uses the linear variational principle to obtain the energies and the wave function. Our first topic is to look at the diatomics. So, when I say diatomics, of course, I can extend it to any other set of atoms, but I have the elements in the second row of the periodic table in mind. For example, if I consider oxygen atom, the electronic configuration of this atom shows that I have got 2 electrons in 1s, 2 in 2s orbital, and got 4 electrons in 2p. So, therefore, if I want to form a bond involving an oxygen atom, so I can consider, let us say, carbon monoxide or oxygen molecule O2. When I do this, I would consider that the oxygen atom would carry these orbitals with itself to form the chemical bond. So, therefore, according to molecular orbital theory recipe, I must take these atomic orbitals and construct the linear combination of atomic orbitals as my trial function or guess function. So, when I consider this oxygen atom, you see I wrote 1s, 2s and 2p, but I know that just like hydrogen atom, if I solve the quantum mechanical problem corresponding to oxygen atom, I would see that the oxygen atom, the Hamiltonian would be a Hermitian operator. So, therefore, I have in principle a complete set of basis function, and therefore, in other words, infinite number of orbitals present. So, you know that we have 3s orbitals, 3p orbitals, 3d orbitals and all other high lying orbitals, where in case of oxygen atom, of course, the ground state configuration does not have electrons in those orbitals. So, therefore, we call them virtual orbitals. They are out there, but in normal circumstances we do not populate electrons there. So, electron density is not found in those particular orbitals. So, that is why we call them virtual orbitals. So, now what we see is that we have got the orbitals where electrons are there, and then we also have got the virtual orbitals. When I construct the molecular orbitals, do linear combination, so what should I do? Where should I stop? The point is, we have to keep one particular thing in mind, that in molecular orbital treatment we see that the atomic orbitals, they contribute to the overall molecular orbital. So, therefore, it is necessary that our atomic orbitals overlap with each other, then only there will be a fruitful linear combination of them. There has to be some overlap between them. Now, keeping that in mind, we can say that if there are some orbitals which are too compact, that means their electron density is restricted to a very limited space in the molecule. In those molecular orbitals which are very compact, they would not show good overlap with other molecular orbitals. Which kind of orbitals are they? For example, if I consider the core orbitals, in case of oxygen, the 1s orbital, we know that 1s electron is situated much closer to the nucleus than 2s and 2p. So, in this case, the core orbitals, for example 1s, they do not give good overlap with other atomic orbitals. So, therefore, they are not good choice to consider them in our atomic or in our molecular orbital formation. Of course, we can consider them, we can take them in and see what are their roles, but even if we ignore them, it is not going to affect that significantly. But in real calculations, we do take them by some other means. We will come to that in later part of our course. Now, the other side of the story is at those virtual orbitals that I was telling, 3s, 3p, 3d, 4s and so on. Now, these orbitals are too diffused, right. For looking at oxygen atom, you see that the virtual orbitals are too diffused. So, therefore, the bonding that oxygen will carry out with other atoms, in those bondings, these orbitals are also not going to give you that good contribution, because they are too diffused. In the bonding region, the bonding in the special region where the bonding electrons would be eventually found, in those places the probability of these virtual orbitals becomes less. So, therefore, they are too diffused to consider. So, now we are kind of commenting something about the virtual orbitals who are too diffused, the core orbitals who are too compact. Now, the Goldilocks balance is best described by the valence electrons. So, they are neither too compact nor too diffused, they are just right. Now, molecular orbital treatment says that the bonding can be essentially described in terms of these valence electrons. So, when we are considering the molecular orbital treatment, it is perhaps all right if we consider only the valence electrons or the valence orbitals. Of course, I must tell you, when we do real life calculations on such systems, we do take care of the virtual virtual orbitals. They have a great role in giving flexibility to the molecular wave function, but primary bonding can be described in terms of valence electrons alone. So, keeping that in mind, so now I have got oxygen, I will consider only the valence orbital. So, 2s orbital and 3 2p orbitals, they are 2px, 2py and 2pz. So, if I consider O2 molecule to oxygen, so each oxygen will bring 4 atomic orbitals. So, therefore, total I will have 8 atomic orbitals. So, the trial function becomes linear combination of 8 atomic orbitals. Similarly, if I consider CO, carbon monoxide, that trial function also will become linear combination of 8 atomic orbitals. Now, if my trial function is linear combination of 8 atomic orbitals, I know that I have to now solve a 8 by 8 problem. That means, I have to solve an 8th order equation in energy to get the energies and corresponding eigenfunctions. That is something that will already scare you, because anything beyond second order, by hand solving them is difficult, but of course, if I use a computer, it would be straightforward. But then here in this lecture, we will discuss some other properties that will make us little relieved that even for this system also, perhaps there is a hope that we can solve some things analytically. Let us see what I have in mind. Now, this is the determinant that I have to solve here. One thing is that we have to, whenever we see this equation, we always know that we have to first calculate the overlap integrals, then we have to calculate the energy integrals. Now, here comes the beauty of molecular symmetry. So far, what we have done is that we considered when we were looking at hydrogen molecule, so there were only 2 orbitals, so we just did everything exactly. Now, when I look at the larger system like oxygen molecule or carbon monoxide molecule, I see there are so many orbitals, 2s orbital, 2p orbitals. They also have different symmetry properties. We used some of these properties in our previous discussion, essentially, especially when we were evaluating the integrals with respect to the theta part or phi part. Now, we would will formulate some basic rules so that the calculations become simpler. What it says is that the Hamiltonian of a system is invariant to any symmetry operation of the molecule. So, every molecule, I guess you have some idea about the group theory and chemical application of group theory. So, you know that we can assign most of the symmetric molecule to some point groups. The point groups are characterized by some irreducible representations. They have some symmetry operations that when we do, they have some symmetry properties. So, corresponding to a point group, we have the character tables. We will show some of these character tables while we are discussing this point. So, the point is the Hamiltonian of this system is invariant to all the symmetry operations in a molecule. So, that means it is totally symmetric. Now, when I construct this matrix element, the energy integral, psi I is one of these atomic orbitals, psi j is another atomic orbital, and the Hamiltonian is the Hamiltonian of the system. Now, if I look at the symmetry property of this overall integral, for this integral to survive, to become non-zero, this must be totally symmetric. The product of these three terms, the direct product of these three terms. Now, already I know that the Hamiltonian would be totally symmetric. So, therefore, I necessarily know that product of psi I and psi j, that means the symmetry species that psi I and psi j belong to, the product of them should also be totally symmetric. And when would that happen? That would happen when psi I and psi j both belong to the same symmetry species, or they both span the same irreducible representation within that molecule's point group. So, when the molecule changes, this overall point group changes, the symmetry properties also would change. We will see some of them in our discussion. So, one particular thing to keep in mind, that the energy integrals and also the overlap integrals will become 0 when psi I and psi j do not belong to the same irreducible representation. That is a very helpful thing to find out. Why so? Because we would see, now let us look at, we are considering linear diatomic molecules. So, this is the point group of C infinity V, this is the character table for C infinity V point group. Homonuclear diatomic molecules belong to D infinity H, that is because they have the center of inversion. Heteronuclear diatomics, they belong to C infinity V because they do not have the center of inversion, like CO, one side is carbon, the other side is oxygen. So, there is no center of inversion. From center, if you go left, you will see carbon, from center if you go to right, you will see oxygen. So, there is no symmetry with respect to the center of inversion, but in case of oxygen molecule, you have a center of inversion because from the center when you go left or right, you hit the same atom, that is oxygen atom, you would not know. So, that is why they belong to two different point groups, but here we are keeping it general. So, we are looking at the C infinity V point group. Now, in C infinity V point group, in the character table, you have here in this top row, you have the symmetry elements. The first column represents the irreducible representation. These are the characters in the character table. What you see in the last two columns is what we are going to use. For example, the last two columns tell me the translational, the rotation of the system, different orbitals, what kind of symmetry do they represent. For example, in this character table, you would see that x square plus y square, that would be the total symmetric part of this function. The z will use that for 2pz orbital, x and y we would use that for 2px and 2py orbitals symmetry. Then you see that z square, xz, yz, x square minus y square, xy, they represent the symmetry of the 5d orbitals. So, looking at the character table, we can see the molecule represented by that particular point group, the atomic orbitals of that system spans which irreducible representation. Now, from here we found out that in case of, if I consider let us say oxygen or carbon monoxide, so I have 2s, 2px, 2py, 2pz. So, I see 2s, the totally symmetric it has spherical symmetry. So, this belongs to sigma plus symmetry. 2pz also belongs to sigma plus to the totally symmetric. Px and py, sorry, 2pz belongs to the total symmetric. 2px and 2py, they belong to this pi irreducible representation, which is a doubly degenerate representation, doubly degenerate irreducible representation. Now, so what we have? We have got 4 atomic orbitals. 2 of them have sigma symmetry, sigma plus to be specific. 2 of them, 2px and 2py, they have got pi symmetry. Now, this statement tells me that if one orbital is of sigma symmetry and another orbital is of pi symmetry, then their overlap integral as well as the energy integrals will become 0. Now, what would that imply? That would imply that I can separately treat the sigma orbitals and the pi orbitals. Is that a good idea? Does that do anything good? The answer is yes. It helps us tremendously, because instead of solving now a 8 by 8 problem, what I am solving is a much simpler system, because I will take 2s2pz of oxygen 1, 2s2pz of oxygen 2. So, I have now a trial function with only 4 functions, 4 starting functions. So, therefore, my systems of equation becomes a 4 dimensional 4th order problem, and that is much easier to solve than an 8th order problem. Similarly, when I look at the pi side, 2px 2py of oxygen 1, 2px 2py of oxygen 2. So, I have got these 4 systems, 4 orbitals. I take a linear combination and I solve separately a 4 by 4 problem. So, instead of solving a 8 by 8 problem, 8th order problem, I am now solving 2 number of 4th order problems. So, that is much easier to do than solve a single 8 by 8 problem. Now, this is what we do. Of course, now we are discussing a bit in a bit qualitative sense, but the same thing can be actually done qualitatively, and the results that we are showing have been verified by quantitative estimations. What here I am showing is this very familiar molecular orbital picture of a 2 system. I am just not committing to any particular atom. It's mostly in general you can apply it to one of these second row elements, but there will be some catch. I will come to that later. But now what you see is that I have colored these atomic orbitals of 2s and 2p, 2s and 2p in 2 different colors, one blue, another orange. The blue represents the sigma or symmetry, the orange represents the pi symmetry. So, that means what I am doing is that I took 4 blue states and took linear combination of them. So, I have a 4 by 4 problem. Resulting solution are 4 eigenvalues. Each eigenvalue gives me 4 coefficients. So, that gives me an idea about the eigenvector or the wave function. When I solve that blue part of the problems, not knowing anything about the orange part of the problem, that means the pi systems, I get 1, 2, 3, 4 blue states. They are all sigma states. Now, each of these states that I am getting are linear combination of 2s, 2pz, 2pz, 2s of atom A and at each of these 2 atoms. Now, each of the 4 is linear combination of these 4. By looking at their coefficients C1, C2, C3, C4 for each eigenvalue, I see that which molecular orbital is composed of how much of which atomic orbital. For example, in this the lower one, in most of the cases it would be predominantly contributed by the 2 2s orbitals, 2 2s atomic orbitals of atom A. The other one would be an anti-bonding combination of the 2 2s orbitals, just like we had in hydrogen atom. So, this anti-bonding combination is being given as sigma u, because this molecule has center of inversion. So, u stands for ungerade, a German term which means simply not even asymmetric, and G stands for Gerade or symmetric or even. So, the lower one is the bonding combination, the upper one is the anti-bonding combination. Similarly, 2 sigma G and 2 sigma U are the next bonding and anti-bonding orbitals coming from the sigma. Now, I solve this problem separately and then look at the orange problems, that means the pi orbitals. Now, I have got 2px and 2py. 2px and 2py orbitals, they represent a doubly degenerate irreducible representation. So, that means by definition they are also going to be degenerate. So, px and py, they would not get mixed within themselves. So, in principle I can also solve them separately without worrying about their mixing, because they are still going to give me 2 degenerate pairs, and this is what has happened. 2px, 2py, they give me 1 pi pair, another pi pair. This is the bonding combination, this is the anti-bonding combination. When it comes to pi orbitals, the bonding combination has ungerade symmetry with respect to the center of inversion. The anti-bonding combination has Gerade symmetry with respect to the center of inversion. So, I got this beautiful picture of the molecular orbitals. Now, you will be wondering, how do I put these energy levels? What are they? They come out from the variational calculations. The variational calculation will give me 4 E values, E1, E2, E3, E4 for the sigma part of the problem, and 4 values E1, E2, E3, E4. In that case, it will be E1, E2 will be degenerate, E3, E4 will also be degenerate for the pi part of the problem. Now, I combine them two and then see where my molecular orbitals, and then I start filling the electrons from low lying orbital to upwards. Now, it so happens that the exact value of the energies would depend on the precise value of the sp separation of the atom, degree of overlap, and other things. So, this, while sigma u and pi z or sigma g and 1 sigma g and 1 sigma u, this region as well as this region remains more or less similar for no matter which atom you consider in your second row of the periodic table. But this 1 pi u and 2 sigma g, they can switch their relative position. That means sigma g can be greater than 1 pi u orbital. Mind you, I can identify these two orbitals very well because they are outcomes of two separate calculations, right? And the particular ordering that I show here, this ordering is followed for oxygen and rightwards, that means oxygen, fluorine and neon. Anything less than oxygen, that is nitrogen, carbon, and for the left, boron, beryllium, etc., they would follow a different trend where 1 pi u is lower in energy than 2 sigma g. But their exact values have to be obtained from accurate calculation. The result of those energies would be used to draw these molecular orbital pictures. But even with this qualitative way of explaining the molecule through molecular orbital theory serves many purposes. We can talk about their bonding, we can compare their relative bond order, experimental bond distances, and many other features from molecular orbital theory. I am sure you have done in such analysis in other courses. Here in this course, we want to see that how these molecular orbital treatments, the molecular orbital picture, are a natural outcome of linear variational principle. Now, we extend our discussion to heteronuclear systems. When you have heteronuclear systems, the key difference is now the two atoms have different electronegativity. Now, based on their electronegativity, the relative energies of these orbitals will change. For example, here in this picture, it shows that 2s orbital is much lower in energy than 2s orbital of B is much lower in energy than 2s orbital of A. So, this would suggest that B is a more electronegative atom compared to A. So, we have, let us say, carbon monoxide C and O in this picture. So, one first difference is that the starting orbitals are no longer same. Now, when the contributing atomic orbitals have same energy, the overlap is very good, because the extent of overlap, the stability of the bonding and the instability of the antibonding orbital greatly gets enhanced when the constituent atomic orbitals have same energy. When this energy mismatch is there, that means the two atomic orbitals which you are considering for the overlap do not have similar energy. In that case, the overlap is weaker, and also we see the bonding and antibonding pattern also changes. So, one thing is that I see the orbitals are no longer same to each other, but other part of the story remains same. What is that? That I considered 4 blue states, 2s and 2pz of each atom A and B. So, I solve this linear variational problem, 4 by 4 problem for the sigma states, and I again take the 2p x 2p y orbitals of A, 2p x 2p y orbital of B, and then solve the pi side of the problem, and then finally I obtain a set of molecular orbitals, and I see that the sigma orbitals are contributed only by the sigma atomic orbitals, the pi molecular orbitals are contributed only by the pi atomic orbitals. So, in this way, in this lecture we discuss how we can use molecular orbital theory for diatomic systems, and in particular how we can use symmetry in describing the molecular orbitals. Symmetry greatly simplifies the efforts that we put for molecular orbital theory calculations, and in the next class we will actually go ahead and discuss about larger systems and molecular orbital treatment for those systems. Thank you for your attention.